Hello, welcome to this presentation about the experimental laboratory, the fluid laboratory. I'm Davide Ganello, and I will present you now in these presentations the laboratory itself. So, what is the aim of a fluid laboratory? The aim is for you to participate to a live experiment, and through this experiment, verify and identify any limit of a Bernoulli equation, comparing experiments with theory, analyzing the flow of water through a Venturi tube. So a Venturi tube is a tube that converge and then diverge backwards. So you have a sort of contraction of a flow and then an expansion again of a flow. This is an image of our Venturi tube with underline, essentially, what you will see. What we can see essentially from this flow is the fluid enters from the left, moves towards the right. At the end, the cross-section is very wide, so the flow goes at a certain speed. Then there is a narrowing. In order to preserve the mass, the flow will accelerate. So in U3, the flow will be much higher. Velocity of the flow, then will expand again, reducing the speed. The Bernoulli equations for a steady, horizontal, inviscid, incompressible fluid flow is the following. Pressure, the local pressure of the fluid, P, divided by the density of a fluid, here we speak about incompressible fluid, plus the local velocity of a fluid, square, divided by Q, is equal to a constant. This is the Bernoulli equation for a steady, horizontal, inviscid. It offers no resistance to flow. Important point, okay? Incompressible fluid flow. The definition of inviscid means no resistance to flow, okay? Real fluid, all of them, show some kind of resistance. Imagine water, for example, or other fluid. In other ways, the Bernoulli equation is a way to state that the sum of a pressure energy and the kinetic energy, the velocity of a fluid, is constant. Therefore, the total energy in an inviscid fluid is constant. Energy is not lost through the flow. And wherever the fluid is faster, higher U, the local pressure will be lower. So if we rewrite the previous equation in terms of pressures, we can move rho. We have a term P, that is the local pressure of the fluid, so-called static pressure. Rho U square divided by Q is the dynamic pressure, the kinetic energy per unit volume of a fluid particle. And P total pressure, is the constant total pressure. And it represents the sum of the pressure and kinematic energy. Now, for an inviscid horizontal steady flow, this sum is constant. So the total pressure will remain constant for an inviscid fluid. So let's try to example an example here, narrowing the pipe. So what we have here, we have a flow running through a pipe that gets narrow. So let's start to analyze a little bit. The fluid will accelerate between point 1 and point 2. Why this? First point, an important equation is the conservation of mass. The flow rate through this pipe, narrowing pipe, is constant. This means that the flow in point 1 is equal to the flow rate in point 2. So the area times velocity 2, the area times velocity in point 2 has to be equal to the area times velocity in point 1. Since the area in point 2 is smaller than in 9.1, the velocity in point 2 has to be higher, okay? So since the area in point 2 is less than area in point 1, U2 is higher than U1. Adopting these equations and remembering the rules, Bernoulli equations, it means that moving from point 1 to point 2, since U will increase, pressure in point 2 here will be lower than in point 1, okay? because faster the fluid, lower the local pressure. Okay? Straightforward. And we keep this point. What this means essentially, these faster the fluid, lower the local pressures are very important applications in many elements. A classic example is the effect on a wing of a plane. For different reasons, when we have a wing of a plane with a certain shape, okay, wing shape, a certain profile, the flow, the top of a wing will go faster than the flow on the bottom of a wing. So we will have a higher velocity on the top face. The air will run faster on the top. What does this mean? Higher velocity on the top means that on the top of our wing, there will be a lower pressure versus the bottom of the wing. Lower pressures on the top than on the bottom face. And this will create a contribution to the lift, pushing your airplane upwards, providing lift to the airplane. The motivation for which the velocity on the top profile of a wing is faster than on the bottom are multiple and are quite complex and an interesting field of discussion and analysis. So that's an important application we can see, wing of a plane. But also in our field, there are very important applications. A classic phenomena and an important phenomena is the effect of cavitations in propellers, for example, in water. Let's take a look. The tip, water, the power propellers will move extremely fast. So the kinematic energy will increase, but this means the local pressure will decrease. The local pressures can go so low that at that specific temperature, the water can vaporize, creating cavitations. So you can see here how this phenomena of Bernoulli, okay, can be extremely important. Faster fluid, lower the local pressure. Another classic example is the ground effects in cars. This was used essentially starting from the 70s extensively. And what we can see essentially that underneath the cars, a lot of time we use a sort of venturi tubes, a inverted wing profiles, a very strange wing profile on the bottom of the car. This wing profile created downwards the car, helping to steady the car on the road, increasing the downforce, increasing the pressure downwards. This helps a lot in terms of accelerations and other terms. How does it work essentially? By providing an inverted wing profiles on the wing, it's more a venturi tube, as you can see, a narrowing and then an expansion. The air will enter a certain speed, slow at the speed of the car. It will then accelerate underneath the car, very fast flow velocity, creating a low air pressure area that will push the car down, creating a so-called ground effect. And that's the importance essentially in the design of all the cars underneath component, very common in the car, in Formula One and Formula style car from the 70s onwards. So ground effect in cars, extremely important. In Formula Student also we use and we study this phenomena. And the student design Formula Student car, taking account the ground effect. So we can see now the importance essentially of this Bernoulli effect and the importance of the equations. What is the experiment that you're going to be called to do? The experiment is very important because in these real-life experiments, you will study a flow through a venturi tube, a converging diverging tube, and you will study the Bernoulli equations to verify if it's valid and to verify any limit to the Bernoulli equation itself. An important point is that having a convergent divergent tube, the volume flow is constant. Hence, the liquid will be faster at the narrow point. The volume flow equal to the cross-section area times the velocity. If Bernoulli is correct, at this point, due to the higher velocity, the pressure should be lower. And this is the experiment that you're going to run. The fluid will start from the left and going on the right. There are here 6 manometers. Measure local pressure, 6 points of the tubes. We know the cross-section area in all these 6 points. What is the manometer, essentially? So take a look at first point, velocity of a fluid. The fluid comes in at a certain velocity. You need to calculate the volume flow rate. So knowing the cross-section area, you can calculate the local velocity. And you can analyze the speed of a fluid at different points. At point U3 is the narrowest point, the fluid will reach maximum velocity. That we can calculate. We can so calculate the velocity of a fluid at different points, knowing the flow rate, measuring the flow rate. We can then analyze the local pressures. So how do we measure pressure? Very simple. We use very simple instruments called manometers. Manometers are narrow vertical glass tubes filled with water. And you can measure the static pressure by measuring the height of the liquid inside these tubes. Higher is the liquid, higher is the pressure. Why? Very simple. Pressure the fluid will be subject underneath here will be equivalent essentially to the weight of water that you have inside the manometers. So the pressure in point P1 will be equal to rho GH1. Let's say a zoom in essentially. You can see essentially the 150 millimeters per manometers, 5 millimeters resolutions. And you can see here that is 150 millimeters high. So the pressure in point P1 will be equal to rho GH, with rho is the density of the water, G is the gravity acceleration constant, 9.81. So what essentially happens? If Bernoulli is correct, according to Bernoulli, the static pressure, the fluid enters at a certain speed with a certain pressure. Velocity 1, pressure 1. The fluid will start to accelerate the convergence. Acceleration of a fluid means the fluid goes faster, but this means a decrease in pressure. The minimum pressure and the highest speed will be reached at the narrowest point. It is the point 3, manometer number 3. The fluid then will reach a divergence, will start to expand, the cross-section area will expand. So in the divergent sections, the speed will be decreasing. And the last sections here, section number 6, has the same height and the same diameter and same area, section number 1. So if Bernoulli is correct, pressure in point 1, the pressure in point 6 will be equal. Okay, and Bernoulli, let me discuss, is an equation studied and defined mathematically for envisaged fluids. That's according to Bernoulli. Then we can run the experiment. The first and last sections will have the same cross-section area, same velocity. Hence, since the total pressure is constant, they will have the same height, the same pressure. You will check this in the experiment. Notice maybe already from this little image that you can see there is a little gap here. Pressure goes up, but it doesn't go all the way up to the top. Why? We discuss in Bishid. So let's take a look at a little bit of experiment. First, we set up the Venturi tube. That's done with the demonstrators. So you record the experiment, the static pressure of the 6 magnetometers. You repeat the measurement 5 times. You want to repeat the experiment so that you know that you are. Because you don't have a measure if you don't have one value. We will speak later on in these lectures about the importance of statistics. And then, of course, in order to measure the velocity inside, we have to know the volume flow. And using a jug, you will measure the time that you need to fill a jug, and you also repeat this one multiple times. For volume flow, you know the cross-section area. It will be provided to you. You can calculate the speed at 6 sections. Using a Bernoulli, you can calculate the theoretical static pressures, and you can compare the theoretical static pressures with the experimental data, charting the results. And then you can discuss any deviation and uncertainty in your data, based also on the notes. So check timetable sessions, when to come, 1 session per student. Attend, do not miss your lab. Before the experiments, watch the videos on Canvas. Bring pen, papers to record the data. Wear suitable clothing. Closed-toe shoes are compulsory for health and safety. And come also with long trousers and closed-toe shoes. Don't climb in flip-flops, please. That's really dangerous. Remember also COVID-19 restrictions that we have that are changing over time, and mask, social distancing. In the analysis, like I say, you can calculate the volume of flow, compare the theoretical results in terms of the equivalent manometer height that's already discussed. So a preview of the results, actually. Number 1. What we do. If, according to Bernoulli, we have red lines, okay? Starting with a certain pressure, energy is not lost because Bernoulli is an inviscid fluid, okay, the theory of Bernoulli. So the fluid will be accelerating, increase in velocity cause a decrease of local pressure. Then in the divergent nose, pressure usually build up again, and we have the same pressure at the beginning than at the end. This is according to the theory of Bernoulli. In practice, we notice something different. There is an increasing difference between the expected following Bernoulli and the measured values. There's a little gap. So yes, after the narrowest point, the divergence pressure will increase significantly. There is a little gap at the end between what theoretically we have following Bernoulli and what actually we measure in the experiment. What do you think this difference comes from? To understand this difference, we have to understand the Bernoulli equation is a fantastic, powerful equation, but start with some simplification of nature. In particular, Bernoulli is for an equation for an inviscid fluid. An inviscid fluid is a fluid that offers no resistance to flow. We can notice that in the experiments, the measured static pressure tends to follow the expected Bernoulli profile. But there is an increasing difference between the expected and the measured values. The measured values are lower than the expected one. Somehow, the energy in the system is lost. And why this? Bernoulli equation assumes an inviscid fluid, a frictionless fluid, no viscosity, no resistance to flow. Real fluids instead have viscosity. Having viscosity, they offer resistance to the flow. And this resistance to flow causes loss of form. in the form of thermal energy. So running through this system, the real fluid will lose energy in the form of thermal energy. In which way? There will be an increase in temperature of a fluid or a heat loss towards the environment. And that's an important point that you understand. So a key point of these experiments is for you not only to appreciate the theory, but also to appreciate the experiment and the differences that we can encounter between theoretical models and the real experiment models. Bernoulli equation is a very powerful equation. In practical terms, if you want more details, we need to correct Bernoulli equations, adding also viscosity in the analysis. Another important point of this experiment is also not only the ability to compare experiment with theory and to understand the limits of one or the other, but also to understand why, when we collect data, how we collect data, and how we analyze the collected experimental data. You've been asked to measure 5 times the static measure of 6 manometers and 5 times the time and the volume to fill the containers to calculate the flow rate. Why do we measure multiple times and not only once? You can just take one measure and nothing more. When we do scientific experiments, we always have to repeat our measurements. One measurement is not a measurement, okay? We measure multiple times because errors, variations influence the measurement process. Hence, we do repeat the measurement. So what is, in fact, if you go to look in the definition of measurement, the official definition of measurement, a measurement is a type, meters, kilograms, a magnitude, a type, weight, distance, a magnitude, 5, 6, a unit, meters, kilograms, and a uncertainty. Uncertainty is very important, okay? In science, nothing is 1 meter long. Something is 1 meter long plus minus 1 centimeters. There is always an uncertainty associated, an error associated to the measurement. A classic example, if we speak about distance, 2 meters is not the proper measurement on its own. You need to know the error of your measures. For example, 2 meters plus minus 0.1 meters is a measure. And that's very, very important because, for example, let's imagine that I have a ruler, okay? And this ruler has a resolution of 1 meter. Yeah, it's a very strange ruler with a resolution of 1 meter. So it goes 0, 1, 2, 3, 4, 5, 6 meters. And I start to measure a class of students. Every single student, by approximations, is 2 meters. So at the end of the day, we can end up that the entire class is 2 meters with no variations. Everybody is exactly the same height. Well, that's improper. Why? Because the measuring tool that we were using had a very poor resolution. Of course, the entire class will be 2 meters plus minus 1 meter, and that's fine. That's a correct measure. It doesn't give you much information, but it's correct. Any individual measurement is subject to a certain uncertainty, a certain error, and this is linked to the measuring tool resolutions, the operator errors and limitations, unwanted environmental conditions. Thermal changes affect the dimension of the system, of the apparatus even. So some rain, humidity, and also to the variability of the object itself. The object can change over time. So as part of this module, you will learn the basics of measuring. So you will learn 2 important points. You will record the resolution of a measuring tool, okay? And you will repeat the measure multiple times. And from the repeat of a measurement, you will extract two important values: the mean value of your samples, the average value of your samples, okay? And you will identify the so-called sample standard deviations. A more detailed analysis of the concept of error is outside the scope of experiments. So I give you just a link of a very nice publications from NPL. It is publicly accessible about the concept of measurement metrology. Standard deviation of a sample is a way to identify the spread of your data, okay? You're here provided with the equation to follow. So to use the standard deviation of the samples, it will tell you essentially that if all your measurement tend to concentrate over the average value, you have a low standard deviations. If instead your measurement goes all over the shots, over the wide range, you have a high standard deviation. And now to calculate the sample standard deviations, there are simple technique in Excel, sample standard deviations. But I write here the equations where X is your measurement, okay? X with a dash is the sample mean, average of your samples. N is the number of the samples, in your case 5. You repeat 5 times the experiments. By this, you can calculate your standard deviation of your samples. Okay? To have. Note that also Excel has a standard deviation of a sample available these functions. A question also in exams also, what are the sources of uncertainty that we have to deal with? There are a lot of sources of uncertainty, and you are more than happy to look for different sources of them in discussing also with the demonstrators. So let's take a look. If we watch, essentially, when we measure the manometers, measurement the height of the manometers, possible source of influence that influence the results as the fluctuation of the power pump flow. So the water pump maybe is not perfectly constant. This creates some oscillations up and down of our line, our pressures, and this oscillation affect our measurement. There is also a capillary meniscus. Surface tension creates a capillary meniscus. So the line of water is not straight, it has a little concave shape. And this concave shape makes us ask, where do we measure exactly the height that we want to use? There is also parallax errors. Depending on where you watch and from the angle of vision, you can measure different readings, depending on your angle of your eyes in relation to the measuring tool. I can also identify more and more possible other sources of uncertainty. But not only the measurement of the manometers is subject to uncertainty. As part of an experiment, you're going to also measure the time that you need to fill a jug of water. And that's also subject to uncertainty. For example, there can be error in timing by the operators, difficulty in reading the water levels in the jug, such as parallax errors and other errors, imprecisions in water collections, error in the timing of when you collect or not the water, and the fluctuation of pumps and other elements that could influence the flow rate of, and so the jug filling and its effect. So, what essentially happens now? To complete the fluid laboratory, very simple. You expect the first is go to the laboratory sessions. You are expected to complete the handout with experimental data. The handout is downloadable from Canvas. You can fill up the handout, it guides you in the solutions, okay? But so, essentially, we will discuss more in details during the experimental lab. The experimental lab lasts only 45 minutes, so please arrive in time. No late arrival will be accepted. So the Bernoulli equations is a very powerful equation. So for example, how to measure the speed of a plane? If you take a look at any aeroplane, okay, you will see on the front or on wings in different spots, little tubes coming out. These are called pitot tubes. And they're used to measure the speed of an aeroplane in the air. So they're very strange tubes that have two holes, essentially. One front hole, 0.2, and one on the side, 0.1. So moving, while the aeroplane moves in space, you move in, in airspace, in atmospheres, you have air hitting our pitot tubes frontwise. So the speed, air in 0.1, will have a speed of more or less the aeroplane, okay? Assuming in relation to the atmosphere. In 0.1, so will be 1 atmospheric pressures and U1 the speed of aeroplanes. But the front point of the pitot tubes, the air in here in tube, and will go nowhere. The stagnation point. Suddenly, air entering in 0.2 will stop. The local speed in U2 will become 0. With decreasing speed, the pressure will increase. And what essentially means, if we use now Bernoulli equations, the total energy is the same. So the energy of a fluid 0.2 will be equal to the energy in 0.1. The overall is equal to squares over 2, equal to a constant. So in 0.2, the velocity will become 0. Fantastic. In 0.1, will be instead pressure 1 and velocity of aeroplane U1. We can measure Q and P1 using 2 manometers. By the difference, we can then, through this equation, determine the velocity of aeroplane. And that's how aeroplane determine the velocity. Okay? Through mechanical instrumentations. A quick important note, a final note, horizontal flow. As part of this flow, let me analyze the flow is horizontal. So we have pressure terms and the kinematic terms. In non-horizontal flows, we should also add a potential energy terms, Z. In this formula, complete is the total Bernoulli equations commonly presented. Pressure energy, kinematic energy, and potential energy. In our experiment, the flow is horizontal through venturi pipes. Hence, the potential energy is constant. The Z is the same, the height is the same, and this effect is not accessible. And the terms can be eliminated. Thank you very much. The presentation is now completed.